Perfect. So hello,
Okay.
everyone. Welcome to a new section of Gravitículas. Today's speaker is Gang Lee. Gang earned his PhD in 2017 from Peking University and worked as postdoctoral researcher at National Taiwan University and the University of Massachusetts Amherst. Currently, Gang is an associated professor in the School of Physics and Astronomy at Sun Yat-sen University. He's interested in physics beyond standard model, including neutrinoless, double beta decay, Higgs physics, dark photons, CP violating, and collider physics. So I would like to invite Gang now to tell us all about Lepton number violating from neutrinoless double beta decay to collider searches. So Gang, we're all yours.
Okay, thank you very much. Thank you very much for the invitation. And yeah, today I want to talk about some of my recent works on Lepton number violation from neutrino double decay to collider search. And this talk is based on the papers where I show here, including some recent paper with Sebastian. Okay. So this is an outline of my talk. I will first talk about neutrinos and Lepton number violation. And I will show the result of neutrino double decay in the standard mechanism, and also show the reason why we want to introduce non-standard mechanism. And in order to describe non-standard mechanism for neutrino double decay, we need an effective field theory approach. And then I will discuss the result of neutrino double decay in neutrino mass model, and also other beyond standard models. So on the other hand, I will also show the complementary search for Lepton number violation at collider, including the prone and displaced searches. The first, and let me briefly introduce what we know about neutrinos. In the minimal standard model, the neutrinos are massless, and from the neutrino oscillation experiment, we know that neutrinos mix with each other. And this requires the massive neutrinos. And from experiments, we can obtain the mass difference square. And from and we know that there are two possible mass ordering of neutrino mass, including normal and inverting hierarchies. On the other hand, we also do not know the mass origin, and also whether neutrinos are Dirac or Majorana mass. So on the left, I show the possible origin of neutrino mass, that neutrinos are Dirac fermions, similar to how other standard model fermion to get their mass. If there exists the right-hand neutrinos, there's possible a Dirac mass term. And to explain the tiny neutrino mass, we need a very small coupling, which is a Y nu here. Because of such a small coupling, and the people may wonder whether it's natural enough. So there's a more natural origin of neutrino mass, that if neutrinos are Majorana fermions. And this can be described by this Weinberger operator. And different from the Dirac mass, if neutrinos are Majorana fermions, then the tiny neutrino mass indicates a very large scale, which is a lambda here. So there are two possible origin of neutrino mass, depending on whether the nature of neutrinos. So how can we test if neutrinos are Dirac or Majorana formula? So to answer this question, we need to know the difference of these two, to compare these two scenarios. And people found that if neutrino are Majorana formula, then the Lepton number, which is accidentally conserved in the standard model, will be violated by 2 units. And so it's very important to seek for Lepton number violation in various experiments. So that's why we study, we need to search for neutrino double decay. And if a neutrino is a Majorana formula, then neutrino double decay process is induced. This can be illustrated. This is illustrated in these two plots here. On the left, we show the how neutrino double decay is generated at the quark lepton level, and at this level, this process is induced by the exchange of the light Majorana neutrino. And at no energy level, this diagram can be embedded into the nuclei, where again, so the process shows the exchange of light neutrino, but it happens in nuclei. So this is this shows so this shows that if neutrino is a Majorana formula, then the process can happen. On the other hand, people also prove that an observation of neutrino double decay will imply a Lepton number violation. And this is shown in the black box here. And this Lepton number violation will contribute to the neutrino Majorana mass term. And this is the well-known black box theory. So from this analysis, we know that the search for neutrino double decay will is the theoretical foundation of the search for neutrino double decay is solid. So there are some caveat here. So although the neutrino double decay, although the neutrino mass is generated at the for loop level on the right, so the mass can actually be generated at the no loop level, depending on how the UV composition is. On the other hand, the Lepton number violation responsible for neutrino double decay may only partially contribute to the observed neutrino mass. So we will discuss in more detail for these two caveats. So experimentally, neutrino double decay process is searched in heavy nuclei like xenon and germanium. So this can be described in the process here. So a heavy nuclei like xenon will decay into another nucleus with a different atomic number. And in the final state, we have 2 synthon in action without any neutrino. So in the diagram on the left, we show how the process happens, including the difference of including the difference of energy level. And the decay, the single beta decay is forbidden of the energy conservation. On the other hand, experimentally, we have a large background, which is 2 neutrino double beta decay. And fortunately, the 2 neutrino double beta decay and the neutrino double beta decay have very different energy peak. So by carefully studying the energy distribution, it's possible to distinguish these two signals if neutron double decay happens. So currently there are many experiments looking for neutron double decay. So the most stringent constraint currently come from the common Z. We study the xenon decay into the bar spectrum. And there's another searches, another experiment looking for germanium decays. And these two experiments can roughly set the lower limit of the decay half-life to be larger than 10 to 26 years. And there are also many experiments in the plane. And so these experiments are at a ton scale. And the target of this experiment are to improve the half-life by 2 orders of magnitude. So this about experiment. So in order to interpret the experiment result, we need to understand how the neutron double decay half-life is expressed. Yeah, is how it is expressed experimented, and it can be expressed in, as a combination of a phase space factor, the nuclear metric element, and the effective Majorana mass. And people already know precisely the phase space factor, and this has been calculated very accurately. On the other hand, about the nuclear metric element, the nuclear physics community has the nuclear physics community has gained a lot of efforts, and there's still a large uncertainty of the nuclear metric element, and it can be varied by a factor of 2 to 3. And the question is, how about the effective Majorana mass? In the simplest cases, the neutron double decay is induced by the exchange of light Majorana neutrinos, and this can be described by the Feynman diagram on the left. So the process is induced by the exchange of the standard model W boson and also the light Majorana fermions. So finally, in the standard mechanism, the effective Majorana mass can be expressed in terms of the absolutely neutral mass and also the PMM matrix element. So by considering the neutrino oscillation data, so which constrain the mass difference square and also the mixing angle, so we know that the effective Majorana mass still depends on the lattice neutrino mass, the neutrino mass hierarchy, and also the Majorana phases. So all of these are still unknown. For this reason, the effective Majorana mass, as a function of the lattice neutrino mass, including a large uncertainty, which comes from the unknown Majorana phases. So here I show the result for 2 different mass hierarchy. So the red one corresponds to the normal hierarchy, and the green one corresponds to the inverted hierarchy. And it also includes the current and the future constraint from the common Z and the time scale neutron double decay experiment. The region above the blue and the purple bands are excluded, and the large band come from the nuclear metric element uncertainty. So we can see that the theoretical prediction for neutrino stability for effective Majorana mass are very different, depending on the lattice neutrino mass and also the mass hierarchy. So currently, from the neutrino oscillation data, the normal hierarchy is more favored than inverted hierarchy. So then, we will focus on the red band here. Then we were in a situation that if the light neutrino mass is in the range from 10 to -3 eV to 10 to -2 eV, there will be a light male region. The theoretical predict effective Majorana mass will be no below the time scale experiment. So this is in the standard mechanism. So we also show the result in the plane of the sum of neutrino mass and the effective Majorana mass. So the sum of neutrino mass is expressed in terms of the combination of neutrino mass M1, M2, and M3. So the reason that we show the result in this way is that the cosmology survey can actually constrain the sum of neutrino mass. So firstly, we show the theoretical prediction of effective Majorana mass in the normal and the inverted hierarchy. Then we include the constraint from the current and the future cosmology measurement. So the gray region is already excluded by the Planck and experiment, so which excluded the sum of neutrino mass about 0.12 eV. So in the future, there are some cosmology experiment, including CMB S4, and they will have a very accurate measurement of the sum of neutrino mass. The uncertainty will be smaller than 0.02 eV. So in the plot, I show that the region on the right of the dashed line will be excluded. So by combining the theoretical prediction of neutrino mass in the standard mechanism and also the cosmology measurement, the future cosmology measurement, we'll find that there'll be little room for inverted hierarchy. And in the meantime, if the sum of neutrino mass is in the region around 0.06 eV to 0.08 eV, the theoretic predict effective Majorana mass will be below the time scale experiment sensitivity. So what I show here. Okay, so this is really challenging for observing neutrino double decay signals in time scale experiment. So that's why we consider the long standard mechanism. So here I gave a comparison of these two different kinds of scenario. So on the left, I show the standard mechanism. The amplitude for this process is proportional to the neutrino mass, mu, and inverse proportional to the p square. P is the moment transfer of the neutrino double decay process. So the value is about 200 MeV. On the right, I schematically show the diagram for non-standard mechanism responsible for neutrino double decay. And it can be described by C over lambda to fifth power. And by comparing these two amplitudes, we can find that the contribution from the non-standard mechanism and standard mechanism are comparable if the new coupling is order 1 and the heavy particle mass is order of TV. So this motivates us to study non-standard mechanism in various experiments. So in order to discuss non-standard mechanism, we need the effective field theory approach. So there are 2 reasons. The first reason is that it can describe all Lepton number violating sources systematically. On the other hand, I will show that only by using effective field theory approach, we can consistently describe neutrino double decay. So here I show how to use effective field theory approach to study neutrino double decay. Starting from a Lepton number violating BSM model, we need to integrate out the heavy fields at a different scale. So first, we need to integrate out the beyond standard model fields and obtain the standard model EFT result. And then at the around 100 GeV, then we need to integrate out the heavy standard model fields to obtain the low energy EFT. So which is composed of U quark, D quark, neutrino, and electron. So this is for neutrino double decay only. And at around 1 GeV, we need to use chiral EFT to describe this process. And it includes the degree of freedom, nucleon, and the pi. So at the lowest scale, we need to use many body methods and also evoke nuclear metric elements. So this is a generic picture of how to study neutrino double decay in the EFT approach. And without loss of generality.
Gang?
Yes.
Can I ask you about this effective mass of this term? No, this effective Majorana mass that you defined.
Yes.
Could you go to the slide where you define it?
Yes. Which page?
I don't know, but
go
some
back,
slides. Yeah, I guess so. I mean, I want to understand a little bit this effective mass. How is it its origin? And because I'm a little confused in this. In order to show this plot, for instance, you are in a what is your setup? You are dealing with an effective field theory at that in that for that to construct that plot, or are you considering the minimal extension with a neutrino, Stirling neutrino to the standard model?
Okay.
Do you know what I mean?
So let me go. Yes. Let me go back here. Maybe for this page.
Yeah.
So.
Yeah. So yes, you have this effective Majorana mass, but in what context is exactly this?
Yeah. So theoretically there could be other origin for the effective Majorana mass, and I will include all of the contribution and factorize it in this way. So the G0 nu and M0 nu are the same, no matter whether we are studying the standard mechanism or we include the non-standard mechanism contribution, and put all the other things into the M beta beta. So this is called the effective Majorana mass.
It's pretty
so
general.
Yeah, pretty general. And what I show here in this plot, so the experimental constraint will be independent whether we are studying in a standard mechanism or non-standard mechanism. But the theoretical prediction, the red and the green band, these are the prediction only in the standard mechanism. So if we are studying the non-standard mechanism contribution, I will show later, then we will see that it will change. It will change.
All right, thank you.
Oh, no problem. Okay. So, okay. Yeah, so let me continue. So without loss of generality, I will start below the electric scale. And at this scale, the operator, the effective operator respect the S03 times U1 gauge symmetry. And there are only a few operators which has been obtained in the literature here. And in the literature, they called, they divide this operator into two forms, which are called a scalar operator and a vector operator. For the scalar operator, the Lepton bilinear has a form of E bar E. And for the vector operator, there's additional gamma mu. So, so first, let's look at the scalar operator. So yeah, I just showed the quark-lepton operator below the electroweak scale. And at no energy scale, so at about 1 GeV, which is the chiral symmetry breaking scale, we need to map the quark operator to hadronic operator using chiral EFT. The scalar operator have different chiral transformation property. So we find that the operator O2, O3, O4, O5, and O2 and O3 prime will be mapped to the pi operator. So what I call pi means there's no derivative. And for the O1 and O1 prime operator, they will be matched to the operator including two derivatives. And all for this Lepton number operator, Lepton number violating operator will be shown in the shown in the same diagram. So the only difference is the explicit form of the pi interaction. So this for the pi scalar operator. And because of the different form of the hadronic operator, and we find that for the pi operator, the amplitude is proportional to P2 minus 2, while for the O1 or the O1 prime operator, the amplitude is proportional to P2 0. So the operator inducing P2 minus 2 amplitude is called the chirally enhanced operator, while the other is chiral suppressed. And we obtained that the amplitude of these two, the magnitude of these two amplitude, and the ratio is about 25. So this is a large number, so which will play a role in our phenomenology importantly. So there are other contributions for the scalar operator, which including only the exchange of one pi and an exchange of without any pi. So all of these contributions are currently suppressed, and the amplitude is proportional to P to 0. And for the vector operator, so we find that there are only currently suppressed contribution. So the only contribution comes from the exchange of 1 pi and the contact interaction without any pi. So in the first part, I will show the interplay of neutrino double decay with the cosmology survey and edge searches. So actually, I have already shown that in the standard mechanism, the neutrino double decay signal is challenged by future cosmology survey, which will put a very strong constraint on the sum of neutrino mass. And on the other hand, the Lepton number violating signal is inaccessible as a edge C, because the process as the edge C will be induced by the exchange of light and neutrino. So there will be a suppression of the phase space. So what we have found is that, or we propose that there's a new paradigm in the minimal left symmetry model. So this is a well-known neutrino mass model. So let me talk about a little bit about this model. So this model has a gauge symmetry SU3 times SU2L times SU2R times U1B minus L. And we introduce a right-hand neutrino, which is NR here. And in the meantime, we introduce a new scalar. So after symmetry breaking, we will so the capital phi will developed in this way, where we have V1 and V2. The ratio of V1 and V2 is important in our analysis. So we also have the wave of the triplet, which VL and VR. And the model is interesting because firstly, it provides a lateral region of neutrino mass, including both type 1 and the type 2 seesaw mechanism, to give the UV combination of Weinberg operator. So secondly, is the most studied beyond standard model for neutrino double decay. So there are a lot of work on this subject. And in this works, people study the new contribution, so which is a right-handed counterpart of the standard mechanism. So where we have the exchange of right-handed neutrino and the right-handed double boson. So we find a leading contribution to neutrino double decay from the left-right symmetry. So to show that, we show this diagram. So the Wi and the Wj can be interpreted in this way. So if there is no left-right mixing, so left-right mixing means WL and the WR mixing, then it's the same as what people found in the literature. So the new contribution is comes from the exchange of two WR. And actually in this model, there's a natural left or right mixing. And if there's a left or right mixing, then the Wi and the Wj are actually W1 and W2, which are lighter and heavier double boson. So although the left or right mixing is very small, because it's proportional to the ratio of the mass of W boson and the WR, the mass square, and also proportional to the sin 2 beta the beta is related to the valve or W by W. Although the left-right mixing is small, but we find that it will give the leading contribution. The reason is that if there is a left-right mixing, the currency of the quark operator is changed. So we have the currency involve both left and right-handed left and right-handed currency, and different from the exchange of the purely right-handed W boson. We will get a different effective operator, which is O4 at a no-energy scale. And in carrier EFT, we find that there is enhancement compared to the O1 prime, and is proportional to lambda chi-square over p-square. So we show that this ratio is about 25, a factor of 25. So by including this effect, we restarted the neutrino double decay in the minimal left-right symmetry model. And we show the effective mass in the plane of the sum of neutrino mass, and show the result in the plane of sum neutrino mass and effective mass. So first we show the result for neutrino mass in the normal hierarchy. The dark green region corresponds to the prediction without left or right mixing. And we find that so by including the future cosmology constraint, which is shown by the blue line here, there will be neutral region for a positive signal. And the region is broader if we include the left mixing. So here, by the way, we also consider the current and the future constraint for neutrino double decay experiment, and also consider the HC bound on the WR and the right-hand neutrino mass. So what's more interesting is the case where neutrino mass are in the normal hierarchy. So as I showed before, the current neutrino oscillation data favor the normal hierarchy. And what we show that in the normal hierarchy, by including the left-right mixing, there will be a broad region which can give rise to possible signal in the minimal left-right symmetry model. So this is what we found. So the future cosmology experiment can probably rule out the inverted hierarchy. This is true no matter whether we are in the standard mechanism or in the minimal left-right symmetry model. And there are good prospects for possible signal in the next generation neutrino double decay experiment for the normal hierarchy.
Gang, are you there? Hello? Gang? Yeah, let's wait for a minute. What happened? Oh, it's the audio. Gang, are you there? We can't hear you. Yeah. Must be an internet connection. We can, so you can hear us. Okay, don't worry. We can wait for you for a while. Is the internet connection? Can you hear us? I'm gonna stop there.
See my screen now?
Yes.
Okay.
Go ahead.
Oh, okay. Maybe I miss here. Let me continue. So what we find is that in the minimal natural simulation model, there's a new leading contribution that comes from the chiral enhanced Lepton number violating interaction. So this original from a non-negligible natural mixing. And while in earlier study, these were missed because they didn't deal with neutron double decay using chiral EFT. So this is really important, and I think a new development in the neutron double decay subject. So, however, by itself, an observation of neutron double decay would not point to the underlying mechanism. It can only tell us that there exists Lepton number violating interaction. And this is shown in a diagram on the left. So in order to pin down the mechanism, we need a complementary searching. So this can be improved if we look for Lepton number violation at collider. So where we study the process of proton-proton colliding into two electrons, same sign electron and jets in the final state. So however, the actual signature depends on where electron and jets are reconstructed. So if electron and jets are reconstructed inside the detector, so this is called the prompt signal. And this is the conventional search for Lepton number violation. On the other hand, So there exists the lateral region for displaced lepton and displaced jet. So if there exists a long lived particle, so the long lived particle is a topic that has drawn a lot of attention for different theoretical reasons. And in general, we show the coverage of different experimental detectors in the plane of the decay length, and the mass of long lived particle. In principle, the HC detector, including Atlas CMS and HCB, can cover the whole region of the decay length, but prefer heavy long lived particle. For the forward detector, including phaser and ship, they prefer a lighter long lived particle and a smaller decay length. While for the transverse detector, they prefer a larger decay length. So actually, there have been some plan for the upgrade of HC detector and construction of new detector. So we will take advantage of this phonicity to study Lepton number violation. So in the previous study, we show that the left-right mixing is crucial for leading contribution to neutron double decay. And this can be shown in the diagram on the left. So the left-right mixing is included in this cross. And the same diagram can contribute as a process to the process at the HC. And because of the because that the right-hand neutrino right-hand double boson is heavy enough, and it will enable a large decay length of right-hand neutrino. So by combining these two kinds of experiments, so if both can be discovered, it would pin down the source of Lepton number violation. So including to indicate that there would be stereo neutrino with mass below the MW, and also there is a left-right mixing. So for illustration, we show the sensitivity of long lived particle searches and the neutron double decay in the plane of the right-handed double boson and the right-hand neutrino. The contours, the red contours, correspond to the long lived particle searches in the process I just showed here. Sorry, show here. And so we assume different efficiency of the selection. And in the meantime, we also show the sensitivity of the neutron double decay in a common Z and then a town scale experiment. So the region on the right of the purple and the orange bands will be excluded. So the band corresponds to the uncertainty of nuclear metric element again. So we can see that there is a complementarity between the long lived particle searches and the neutron double decay, both of which can be used to directly probe the left-right mixing. So this for part one. Because of time, maybe I should repeat. So the second part, I will talk about another approach. So in the simplified model. The simplified model will give us different phenomenological insight. So I just mentioned that the Lepton number signal in neutron double decay and edge searches can be uncorrelated with the observed neutrino mass. So we will show a case study. So first, we propose a simple model that induced a chirally enhanced neutrino decay. So this is inspired by the RPV supersymmetry model. So we include a doublet scanner similar to Lepton and Majorana fermion similar to neutrino. And this in this model, we will obtain O2 prime operator at a noisy scale. And this quark Lepton operator will induce leading order pi interaction. And so the Lepton number is violated by the mass term of this Majorana fermion. And as it shows that it can be uncorrelated with neutrino mass because there's additional scalar coupling. So we can set it to be 0 so that it has nothing to do with the edges search and the neutrino decay. So in our work, we study the the correlation between neutrino decay and HC searching. So what we find is that there exists a different region for Lepton number violation. So in the literature, people have studied the region where both the Majorana fermion and the scanner are at the TV scale. And this and what we find is that if exists a large mass difference between the new particle, there exists a region that enable a long new particle. So we show the result in the plane of Majorana fermion F and the effect coupling. And we can see that the region between the blue and the red curve, so which is in the reach of neutrino decay, indicates a large lifetime. So we study in more detail and obtain the result here. So we study different mass of Majorana fermion and show the result in the plane of a scanner and effect coupling. The sign region correspond to the sensitivity at the HC main detector Atlas and CMS, and we also studied sensitivity at the Matusna. So in the meantime, we also show the exclusion ability of neutrino decay in brown and orange. So we can clearly see that the importance of HC search, especially if the Majorana fermion is heavy, and we can see that HC's display searches can probe totally different region. That's a response for Lepton number violation. Okay, this is about the chirally enhanced operator. We also study the chirally suppressed operator, so which is the vector operator. So as we show that for O1, O1 prime, O4, O5, so these are realized in the minimum Laplace image model, and for O2 prime and O3 prime, this is realized in a simpler model that's inspired by RPV supersymmetry. So how about the vector operator? So can they be uncovered in neutrino decay and the collider searches? That's what we want to study. So we have shown that the contribution of vector operators are currently suppressed respect to scanner operator. This can be shown in chiral EFT. However, we find that the ratio of the amplitude between the vector operator and the scanner operator also depends on the ratio of nuclear metric elements. And there is an enhancement in the nuclear measure element. So we actually we firstly find the result, and just 1 day after our paper, there's another paper also point out the same result. Okay, so we so this indicates that actually there is the vector operator can induce a non-negligible result to neutral decay. On the other hand, we studied the complementarity search at the AGC. So we propose a simple model that includes a new scanner, Lepton quark, and Dirac formula. And it will induce the this vector operator below electric scale. So we find that first we do some preliminary study and find that the Lepton number violation scale is below a few TeV. So this is in the reach of AGC. And we find that we just study different scenario. On the left, we assume that the mass of the new fermion and the new scanner are below or equal to 2 TeV. And we can see that the AGC searches are more constraining than the neutrino decay searching. So this is changed significantly if we improve the new scanner mass, and we will see that the neutrino decay will give a strong constraint. So we find that, so this is what we find for the simple model. Neutrino decay can be induced by effective operators that may be uncorrelated with the observed neutrino mass. And the scale of the Lepton number violation is in the region of AGC. And in the framework of similar model, we show that both prompt and displaced signature at the AGC are possible. And finally, the current suppressed mechanism for neutrino decay can be better constrained at the AGC. So this is my summary. So I will stop here. Thank you.
Okay.
Sorry, I use more minutes.
No. Thank you. Thank you very much. It was a wonderful talk. Does anybody want to have a question for Gang? I would like to ask you, out of curiosity, if there are some effective masses constraint for the effective mass of Majorana neutrinos, but for other flavors other than electron, the electron one.
You mean muon or tau?
Yeah.
Right.
Yeah.
Okay.
Such a bound.
Yes. Oh, okay. So firstly, the neutrino double beta decay only search for the final state with electron.
Yeah.
Yeah. So, and on the other hand, there are also other experiments such as mu minus to E plus, and this process similar to neutrino decay. We can define an effective mass, but for mu and E. Such a process is, the constraint is very, there is almost no constraint, so it's very weak. Yeah.
Oh, okay. Okay.
I have a question.
Yeah.
Do you have any constraint on the vacuum expectation value of the triplet due to the rho parameter?
Right. Yeah, we include the rho parameter constraint.
But
yeah.
More or less,
so actually,
remember the constraint? I mean, what does it imply?
Actually, in this paper, we missed this constraint. So we the constraint the rho parameter will constrain the tangent beta, which is the ratio to the W values. And by impose the constraint, the upper value will be 0.3. So this will slightly weaken the sensitivity, but will not change our conclusion. So we update the result in later papers.
Okay.
Yes, thanks for pointing. Yeah.
And about the mass of the W, the extra W, you need, in order to have a large mass, like 70 TeV or so, you need a large vacuum expectation value.
Yes, VR, right?
Yeah, but it means, do you have a reason to have that BEV much bigger than the electroweak VEV? I mean, you need one VEV much bigger than the other.
You mean VR is much bigger than V, right? So you mean?
I mean, yeah. In order to get a mass for the W of 7 TeV, you need a vacuum expectation value of that order, which is much bigger than the 200 GeV that is the electroweak VEV.
Okay. Yeah. So
my question is if you have a reason to have that hierarchy, or it's...
Yes, that's true. So actually, if we go to, if we come here,
yeah.
So actually, as you mentioned, the VR, so which is related to the mass of the data, I think. Then the VR is a large VR guarantees a small neutrino mass. So a large VR is preferred in the sense of a small neutrino mass.
But doesn't it go in the opposite direction? I mean, if you increase the VEV of the triplet, you increase the mass of the neutrino. If you want to decrease the mass of the neutrino, you want to decrease the VEV of the triplet.
Oh, not the VEV of triplet. I think the mass of, mass of triplet. Yeah, why are they in the? Yes, a heavier triplet mass corresponds to a smaller neutrino mass.
Yes. Okay, I see. Thank you.
Yeah, no problem.
I have a question about these simplified models that you showed. You had this, you introduced, for instance, one scalar and one chart fermion.
Yeah.
And my question is, how do you connect those states or those fields with this neutrino, Majorana neutrino?
Okay.
At the Lagrangian level?
So you mean this simple model?
Yes.
Yeah.
Yes,
so what I want to show for this simplified model is that the Lepton number violation can be uncorrelated with neutrino mass, the observed neutrino mass. And so here I show the diagram. The neutrino mass can be generated at one loop level. However, it depends on a coupling, which is lambda HS. So we can choose this coupling to be small enough so that it will not excluded by the neutrino mass, but it can still indicate the signal, Lepton number violating signal, both at both in neutrino double decay and then the HEC search.
Okay.
Yeah, thank you.
I see. Thank you.
Thank you.
Gang?
Yeah.
So a question: what is your let's say criterion to differentiate a prompt and a long-lived particle? Like, is that a criterion that depends on the detector, something like that?
So you mean how to define?
Yeah, how do you define a long-lived particle? Do you have a criterion, like, let's suppose that C tau for such particle is 10 to the minus 7 centimeter or greater?
Yes,
a
yes.
long-lived particle. Do you have a criterion like that, or?
Right. So so let me go here. So for instance, for this study, so actually we use a semi-analytical formula, and we require that the decay length should be in some interval, and it should be larger than some value and smaller than some value. So only this region can it be reconstructed.
Which one?
Both for the Alta and CMS and also for Matusna.
Right.
So I think.
Oh, I see.
So it should be, the decay length should be larger than some value. Then it defines what a displaced search is.
Okay,
right?
I
And
see.
it should be smaller than some value because the detector has finite size.
Yes.
Yes.
I see. Okay. So this.
Okay, thank you.
So if you go to particle data group, you can see in the section of the Higgs scalar particle searches that there are some bounds on the masses of new scalars, of charge scalars, which are around of 80 GeV or so. So those bounds doesn't apply in your model.
Yes, right.
Because
so
those are prompt.
Yeah. So here we assume that the S does not develop a vector, so it can escape this constraint. So we also check that if it develops a very tiny valve, it can still satisfy the constraint. So we check that.
Right.
Okay, thank you.
Perfect. Anyone else? If you have a question. All right. So I would like to thank us again to Gang for the talk.
Okay,
it was a wonderful talk. And I would like to thank everyone else as well. And we will see each other next seminar, hopefully, with, if I'm not mistaken, this is the turn of Bastian.
Yes.
Perfect.
Okay, thank you very much.
Thank you very much, Gang.
Thank you very much. Okay.
Thank you, Gang.
Bye.
Thank you. Bye.
Thank you, everyone.
Bye-bye.